All right, let's get a bit more complicated here. So we've got a pipe here. It's got some sort of caps on the end, whatever. It has some torsion applied to the caps, I guess probably while they're tightening it, I guess. And it has some sort of external axial tension applied to it as well. And then the inside of the pipe, you also have a pressure of 500 psi. So inner diameter of the pipe is 0.5 inches. Its thickness is 25 thou. So we want to figure out what sort of principal stresses occur on the surface of the pipe as well as the maximum shear. So the various loads on the object. We want to make sure that we don't miss any. So we're going to have torsion. We're going to have the axial, and then we're going to have stresses due to the pressure. So the hoop stress and the longitudinal stress. So let's start with the axial. That's usually fairly simple. So the normal stress caused by an axial load is just the load divided by the area. Area in this case, pi times the outer radius, the radius of the outside squared, minus the radius of the inside squared. So again, the inner diameter was 0.5 millimeters, sorry, 0.5 inches. So the inner radius is 0.25 inches, and then the outer radius is just that plus the thickness of 0.025, so 0.275 inches. So that gives us a cross-sectional area there of 0.0412 inches squared, which means that if we take 200 pounds and spread it evenly over that space, we get 4.85 ksi. Hoop stress is next. So our hoop stress is going to be the internal pressure times the internal radius divided by the thickness. So 500 psi times the 0.25 inches divided by the 0.025 inches of the thickness. So that gives us 5 ksi. Longitudinal stress is always just half of your hoop stress, so 2.5 ksi. Next are shear stress. So we're going to need to figure out what J is for this. So again, J is going to be half is pi over 2 times the outer radius to the fourth and minus the inner radius to the fourth. So plug in those numbers, you end up getting 2.58 times 10 to the negative 3 inches to the fourth. So then we can use that. The torsion that was applied was 12 pound feet, I guess, pound feet. So I want to convert that to inches, pound inches. So, throw in the conversion factor of 12 inches per foot, cancel out your feet, and then times the 0.275 inches, that is the outer radius, because again, we always know that the maximum shear stress when torsion is applied always happens on the outside skin of the very most outside radius of the thing, because it's directly proportional to the strain, and the strain increases linearly from the center of rotation. So anyways, that's 0.275 inches, and then divide that by our J, and then we'll cancel out units. So this inch cancels out 2 of these inches, leaving us with inches squared on the bottom there. And so what we're left with is in units of pound per inches squared. So plug this in, you're going to get a reasonably large number. So I converted it to KSI, so that's 23.16 KSI. So a fair amount there. So that's the shear stress. So if we are going to be looking at a small element on the outside of this pipe, I kind of just arbitrarily chose to kind of take one, if we, and I'm going to draw it bigger here. So here's the pipe. It's got that little cap thing. Kind of on the outside in the middle here. No, I didn't scroll up far enough, did I, for drawing that? Yeah, so picking a spot kind of right here. So again, with the orientation that we're working with, I'm going to use X in this direction, Y is going to be in this direction, and Z would be out this way. So the directionality of the stresses that we did calculate, we know that the axial will be in the X direction, as will the longitudinal stress from the pressure. So those two things add together. They're both positive. So 2.5 plus 4.85 KSI gives us 7.35 KSI. And then we've got the stresses in the Y direction. So again, the only of those loads that causes stress in the Y direction is going to be the hoop stress. So that'll be 5 KSI. And then we have the shear stress. So the directionality of the shear stress is kind of it's going to be based upon how this is twisting. So again, if we look at a little cube kind of in the center there, we're applying a twist this way, which means that on the left side of the cube, we're going to be applying a force that causes that left side of the cube to want to move upwards, which means on the other side we need to apply a force that resists that, and then here and here we also need to have forces acting in the proper directions. So anyways, so we got those, and we've got the tensile stresses in both the X and Y directions. So when we're doing our Mohr's circle, again, the first thing we do, now that we have the X and Y, now that we have our element defined, we just need to kind of figure out where stuff is on Mohr's circle. So again, our center of Mohr's circle is going to be based upon the X and Y stresses. So our sigma X plus sigma Y divided by 2, so 5 plus 7.35 divided by 2, that gives us 6.175 KSI. Our radius, again, is going to be based upon kind of where our known spots are. So we just need to figure out, so we know that the Y component of this distance here is the 23.16 KSI that we calculated for the shear stress right up here. So that's that. And then the X component, that's just going to be based upon the position of the known. And again, I like to use just the positive X face because, I don't know, you got to pick one of them. You got to pick one of them, and I like to use the positive X face. So the 7.35 minus its distance, minus the location of the center. So take the square root of 7.35 minus 6.175 squared plus 23.16 squared gives us a 23.19 KSI radius. So from that, we can calculate what our prime stresses are going to be. So our first one's going to be the 6.175 plus that 23.19, gives us 29.37 KSI. The next one's going to be our 6.175 minus that radius, and it gives us negative 17.015 KSI. That's there and there. And we need to find out how to get from there to there. So again, we just need to figure out what this angle is here, because that angle will be double the amount that we need to rotate in order to get rotate our element in order to get to our prime axis. So again, we'll calculate that. Our twice our theta prime is going to be equal to the tangent of the 23.16 divided by that the 7.35 minus the 6.175. So that gives us a theta prime of 43.5 degrees. And to get from here to here, we need to rotate clockwise that amount. So if we're rotating clockwise, then basically we are, we end up with an element that's located like this. And if we want to kind of know which one's which, again, we are starting out with this. Let's see, if we'd started out with this face here being the one that had the 7.35, and then we rotate clockwise, which means that this face here, after it gets rotated, it corresponds to this face here. So this face ended up being this prime axis here. So this is the one that has the 29.37 tensile stress, and the other two faces, and obviously the one opposite to it, and then the other two faces are the ones that have the 17.015 compressive stress on them. Alternatively, we may not be worried about the maximum normal stresses. We may be worried about our maximum shear stress. So back up to our Mohr circle. Instead of going this way, we want to get to our point for maximum shear. We just need to go this way a tiny. We just need to rotate this counterclockwise a tiny little bit. So again, if this rotation here was 43.5 degrees, then this rotation here needs to be 1.5 degrees. So we're only moving a tiny little bit. And when we do so, all the faces have a 6.175 KSI tensile stress applied to them, because that's the x coordinate of our of the center, and they all have a 23.19 KSI shear stress on them. And again, we started out with the directionality of the shear stress like this. And since we're only rotating a tiny little bit, obviously nothing really changes with the directionality. So it's still going to be like this. So that's our maximum shear element. And that is that.